Thank you. Sorry, I have to go switch to a Mac here, so it'll take a couple of seconds, hopefully not more than that. Ta-da! Okay. So thank you for sticking around, either because you're local or because your flight is too late. So I'm glad there is still a few of you left here. Today I will talk about the microscale electromechanical characterization of the PM and PT single crystals. And I would like to acknowledge especially Lee and Steven from Georgia Tech, the students that did the work, as well as contributions from Dr. Gaponenko for the machine learning techniques, Rama that helped us with at least one set of measurements at Oak Ridge, and Shujung Zhang from Wollongong University that provided the wonderful single crystalline samples. Hopefully by now I don't have to tell you why we care about the relaxer ferroelectrics with their very high electromechanical response, and pretty much the fact that still 20 years later, it's still controversial where this very high response comes from, given that depending on what is the goggles that we are putting on for looking at these materials, we come up with a different answer. So we have been over the years associating this, at the very least, these very high responses to mesoscopic heterogeneities in these materials. And we have been talking about polar nanoregions, chemical nanoregions, and coexistence of multiple phases, specific at the morphotropic phase boundary, which you can switch between with the electric and mechanical fields. So these are the goggles we have been using over the years. X-ray diffraction clearly gives us some solution to what is going on in the material, especially structurally under applied fields. Unfortunately, it's somewhat of a surface, surfaces being very relative who you talk to, characterization technique. We learned a lot more about the local dipole-dipole correlations with the neutron scattering. However, although this technique gives us very local structural information, it's really averaged over a very, very large volume. And then, of course, we can do macroscopic characterization of the functional response, and we can correlate it to those external fields. However, these length scales have absolutely nothing to do with the length scale at which the properties are born. So over the last decade or so, piezo response force microscopy has been taking really ground for analysis of the properties of these materials at the small scale. So you take an AFM tip, a cantilever, and you apply electric field directly to the sample, and you figure out what is happening there. And we have used, for example, this before over the last 3 to 4 years in collaboration with Oak Ridge to show how we do have a very large contribution from the electrorestriction rather than any extrinsic domain wall or phase boundary motion in these materials, especially in the 28 PT composition. And that we can actually track through the contact resonance frequency any eventual phase transitions that happen under our applied electric field, and that results in a very large softening of this resonance frequency corresponding to this enhanced electromechanical response. So as you can see, this is the red curve with respect to a regular ferroelectric transition within the same material. So what we are proposing to do in this work is actually look a lot more coherently across the phase diagram at what happens in these materials. We will be looking at single crystals, all of them cut along the 0,0,1 axis, and we go from the one end member, the pure PMN, up to the 40% PT, which brings us across the morphotropic phase boundary into the tetragonal side of it. And what we'll do is look at the really polarization state of the material, but also then go on and look over, and this is done over a 2 by 2 to up to 3 by 3 micron square areas. And then we take the same area and divide it into grid points, 50 by 50, and then for each of those grid points, we perform switching experiments to look at the piezoelectric response, as well as apply pulses, and then figure out how the piezo response changes over time. And we do that with an triangular envelope, so we apply positive pulses, and then followed by negative pulses, and then we figure out how the response changes over time, and we call this the relaxation experiments. So very quickly, looking at actually how the sample looks like in terms of piezo response and how these are distributed within the spatial resolution of the tool, we can see that we start from PMN, from what we would expect, in fact, this kind of mottled contrast, even in the piezoelectric response. And then by the time we add already 10% PT, these start having some structure to them that start looking like more ferroelectric domains. By the time we are looking at the morphotropic phase boundary compositions, and on the top we do have out-of-plane piezoelectric response response, and then the lateral piezoelectric response, you can see that we do have a very high density and very high response, actually, of the piezoelectric response, of the piezoelectric functional characteristics. And at the end, when we go to the tetragonal side, we do have structures that really look like ferroelectric domains. In fact, if you do look at the phase of the response, again, we reproduce similar things, minus the fact that I really want to show you how we have a very, very high density of domain structures really in the morphotropic phase boundary region. But when we go to the grid points, now suddenly we are looking at 2,500 points of data within that single 2 micron or 3 by 3 micron area that we were characterizing earlier. And this right now is just really the mean response, average over all of those 2,500 points at the highest polling, basically, if you want, voltage that has been, over the range of the pulses that has been applied. And the interesting thing you can notice that while you would expect that after applying a pulse, the response, piezo response, would relax over time, that's not always the case. It does indeed mostly relax over time, but at times it also shows this polling behavior, which is extremely predominant here, seen in the pure PMN cases. So while this looks pretty, we would like to look at it more quantitatively. So what we use is an exponential, a stretched exponential to fit these curves one by one. Well, we don't do it manually, thanks God, but we're doing it with the computer that does it for us with the code. So we will look at a saturation value, A naught, how much the response is changing over time, R values, a time constant tau, and the stretch exponential coefficient. If you start looking at the histograms here of the distribution, we again quickly see that we do have a bimodal distribution. We have positive R naughts and negative ones, which again correspond, as I said earlier, to relaxation and polling behaviors. But even within the samples that show only relaxation, there are two kinds of relaxation mechanisms that have two very different centroids. When we look also at the stretch exponential, we do find that there is a bimodal distribution. Those that the behavior really falls under a simple exponential, that's a beta equal to 1, and a very wide distribution of betas. Now, this is interesting for us because, in fact, beta is a measure of the disorder in the sample or the disorder in the distribution of these relaxation time constants. So these are theoretical work done before. If you get a beta, you have a very narrow distribution, and if you have a beta that goes closer to 0, this distribution is going to be wider and wider in space effectively. And because we are not good with our eyes to just compare histograms and derive any kind of behavior from that, we try to leverage machine learning techniques to try to identify the underlying phenomena for what we have been observing. And in this talk, I will try to concentrate really on two approaches, the principal component analysis and the non-negative matrix factorization. The principal component analysis and NMF, they are both based on a linear combination of an underlying component, whatever they find, with the difference that the top technique does consider positive and negative trend to be perfectly equivalent. So cannot distinguish between a polling and a relaxation as long as the characteristic values seem to be the same. NMF allows us to do that, but consider the data have to be non-negative and then the resulting components to be non-negative. So it means that NMF is really good to look at the relaxation data, but is not good for looking at switching. For switching, because the data change trends in the positive and negative direction, we have to go to the principal component analysis. And here you can see the difference. If I use PCA or ICA that I didn't mention, I actually get two different relaxations when I'm supposed to find the relaxation and the polling, while NMF correctly identifies the underlying components. So if I look at the first component, that relaxation really underlying across the phase diagram, and these are not really to scale because the different methods use different timestamps, you can see that I go from something that is relatively uniform at PMN with, again, somewhat of a model to something that looks like reproducing the high density of the domain structure to something that is really reproducing the domain structures in the ferroelectric composition on the tetragonal side of the MPB. And then that this time constant for the morphotropic composition is much smaller than any of the other relaxation behavior. If I look at even the second component, and regardless of the fact that some of them are going to be polling and some of them are going to be relaxation, the tau is still the smallest in the PMN 28 PT. And in fact, it's almost exactly an order of magnitude smaller with respect to the tetragonal composition. These are all presented to you at the highest polling voltages that we use in any set. So we really expect at this point to sample to be polled, and we are looking at the response. So if we look a bit more closely at the 28 PT case to see what is happening, you can see that these behavior are basically very consistent. You start increasing the maximum value till you have gone beyond the coercive value, and then it kind of tops off, and then the relaxation becomes stronger. But that happens also for the polling. So we're wondering what is going on. The first thing we looked at is where do these different components appear? The polling component actually matches really well in locations with the locations that we have observed a very high piezo response amplitude in the sample itself. It doesn't necessarily produce anything special in the phase, which would be the polarization more correlated to the structural changes in the material itself. So we tried actually to figure out what might be happening here, and because it was correlated to the very high response, we remember our own previous work for the very high response, which associated this with the field-induced phase transitions. So we try to correlate that to the switching response, and as I told you, our method does not distinguish between up and down and positive and negative, so this might seem more familiar with the butterfly hysteresis loop. So we try to do principal component analysis for switching, and we get two responses: the typical ferroelectric butterfly loop, and then another component that has large increases corresponding to the field-induced structural phase transition in the material. And lo and behold, that component actually results at reducing electric fields in an actual increase in the piezoelectric response of the material, which actually was supported by the phase field modeling in the samples too. So is this really true? If that is true, we should see the signature of it in the resonance frequency of the material at the transition. So if you look at the position that a single pixel data point, this is a very strong relaxation port, so it has this component for relaxation substantially larger than the polling one. What we do see is that there are the curves response, of course, is substantially noisier, and Salje and Jim Scott presented earlier about how these jerks can happen in the material. But the interesting thing is once things start switching, it switches, as you would expect, back and forth for each pulse. And when you look at the resonance of the sample, this continues to harden over time, and it's polling somewhat more. And the changes are really, really small. They're probably below 1% in the resonance frequency change. Now, if you look at the strong polling location, something very interesting happens. Well, it switches and it changes. The amplitude goes substantially higher within some of the first few polling pulses, and it corresponds to a phase change. And beyond that, the phase doesn't change anymore quite. But this corresponds also to a very large change in the resonance frequency. This is approximately 15%. Here it is, 15% softening in the resonance frequency. And beyond that, it can harder still, but is much, much larger and wider range that we have observed for the simple relaxation behavior and simple ferroelectric behavior in the material. So to us, this was a confirmation that this could indeed be correlated with those phase transitions. One thing that is interesting that I want you to notice here is that if I have kept myself just to the mean value of all these 2,500 data points, which would have been the equivalent of making a macroscopic measurements, I would have got data that are extremely different by looking at 2,500 data points and looking at the average data from those. If I fit every single curve and I look at what I find with respect to the components, I get, for example, betas for the polling that is almost strictly around close to 1, and that are substantially larger than any of the mean values that I would have found. Similarly, the trends are actually very different for the time constant in the material itself. So for us, this was really a confirmation that you should be looking at more data points and then from those extract fundamental behavior rather than simply looking at an average of the data. In fact, when we go through across the phase diagram to more and more lead titanate content, you can see that this polling remains, although in one of the directionality starts to fizzle out, and that might have to do with an internal bias in the sample that would allow us to have this behavior in one direction, but not necessarily in the other. And by the time we get to the tetragonal side, you can see that this dies in the negative poles right away, and then it becomes another relaxation behavior, and this kind of dies away later on and also becomes a relaxation behavior. Does it correlate with anything else in the material to give us some more information? Well, it somewhat does. If we look at the switching behavior and at the component of switching, what we find is something that might or not really be ferroelectric, something that is really looking like a ferroelectric piezoelectric butterfly loop, and something that might be a very strong ferroelectric, but it's strongly biased also. So the magnitude of this is substantially higher than the proper ferroelectric, but it's very large internal bias, so it hasn't really come out towards the full switching in one of the polarities. One thing that is interesting is that these two identify the high responses, but somewhat in a complementary fashion. So we have regions that is very high ferroelectric, but symmetric, very close to regions that are very high ferroelectric, but are asymmetric, and they have internal biases effectively in them. And again, they don't necessarily match with anything that we find in the polarizations, which to us brings on a question mark if this is something that is related not necessarily to polarization and structural changes, but more to the underlying chemistry that is in the material itself, because that's what we cannot see in the PFM. And then lastly, when we try to correlate those relaxation behavior to the regions for this switching behavior, what we notice that is somewhat, of course, expectedly, the relaxation really follows this symmetric ferroelectric-like behavior, while the poling regions really follow the possibly ferroelectric but very strong internal bias regions. So with all of these, and this is the initial really part of this work, I want to underline that for decades, effectively what we have worked upon has been big chunks of a single crystals when we have been successful in producing them, and made conclusions based on an average response at length scale that not necessarily are correlated to where the functionalities are born. But we can use that same single sample and extract statistically a lot more information about the functional response and learn a lot more about these materials where the functionality is born at much smaller length scales. Thank you.
Thank you for a very nice talk. And any questions?
Wow, so many data and new information.
And so much fast talking, yes.
I'm thinking you suggest that the different behavior in different places could be related to the chemical heterogeneity. Another possibility is that you may have the same material, but something like domains, so the different crystallographic orientation. Imagine a ferroelectric domain, which once you are looking along the polarization, one perpendicular to it, once you would expect out-of-plane piezo, the other case you would not. So my question is, did you ever thought or try to compare or look in the literature how it would be in the thin films, where, for example, I would have some kind of texture?
So, first of all, we wanted to remove that issue, so that's why we worked with the single crystals, right, 001 cut single crystals. And you're absolutely correct. It could be related with the domain structure, so what happens if I have already a polarization that is lying in plane and I'm pulling that one up? We could not find a direct correlation comparing both with the out-of-plane and the in-plane polarization effectively. That's a phase of the piezo response that you observe is directly correlated with the out-of-plane and the in-plane polarization components. And we could not find really a direct correlation. There might be specific locations, but percentage-wise, there is maybe 5 to 10% correlation with the polarization where you would have to have a very high density of polarization change, or basically could be related with the structural changes in the sample, versus locations in which we do not have any correlation. In fact, you would have a very uniform polarization both in and out of plane, and then suddenly you do see very different behavior, which to us means it doesn't seem to be really correlated with the direction of polarization pre-existing one. It could be more correlated with something else that we cannot see with PFM, and chemistry we cannot see with PFM. To full disclosure, what we are trying to bring this is a start with PFM, create references, bring it to something that we can structurally analyze, so do mapping with hard X-ray, and then bring it into TEM, and then cut that same piece of TEM into atom probe tomography or whatever else. So we really have a wide understanding, really a mesoscale at the small scale understanding of functional, structural, and chemical all together. That's it.
Thank you again. And the last speaker of this session,
he's using his own.
Dr.